Hello and welcome to day 3. Woohoo! We're going to be going over logarithmic functions and their graphs, which I know are your favorite, so you're just going to love every second of this video, I'm sure. You can see what our goal and purpose are for today. We're just trying to deal with basic log expressions and their graphs so that we can just keep making our function library a little bit better. So we start off with the definition of what is a logarithmic function. Okay, so we discussed this way back in chapter 1, that if a function passes the horizontal line test, then the inverse of that function is also a function. So an exponential function, which we know, if this thing will actually write, so here's our exponential function, it passes the horizontal line test, which means that the inverse of an exponential is going to also be a function. And it just so happens that that inverse is a log. Okay? So here we have just it written out. We would pronounce this as log base b of x. Okay? And we have all these fun properties that go on here that basically come from the exponential when we do an inverse of it. So you have the inside of a log can't be negative. The base has to be positive, and it also cannot equal 1. And that gives us that f inverse would equal log base b of x if and only if the original function was b to the x. So I'm going to do a quick little example with 2 of these. So I'm going to let f of x equal 2 to the x power, and then I'm ultimately going to do the inverse of that. But first, let's just say, what is the domain of this? So domain of not rational, what are these things? Exponential functions. Those are all real numbers, and the range is that y has to be greater than 0, because remember that we got that horizontal asymptote right there. So if I switch colors, maybe if I have the inverse of x is going to actually be log base 2 of x, the domain and range are just going to actually switch. You remember that that property happens when you have inverses, that they just switch back and forth. So this one will now be x is greater than 0 because that's what the range was for the exponential, and for this one the range will be all real numbers because that's what the domain was for the exponential. All right? Now, what's really, really important for you to know in this little section here is what I'm about to put way over here. So we have y equals log 2 of x is the same exact thing as having 2 to the y power equals x. Okay, these two things are interchangeable. One is in log form and one is in exponential form. And if you can figure out how to switch from one form to the other, that's going to make this entire chapter really, really easy, essentially. Okay, so this is like super important. I'll put some stars around it so you know. Alrighty, I'm going to do some examples. If you want to skip this section because you feel like you know how to do them, feel free. Ooh, examples. All right, let's pick a fun color, purple. All right, so there's a very specific way I want you to actually read these logs when we're trying to just kind of say what is log base 2 of 32? What does that actually mean? So that's how I pronounce it out loud, log base 2 of 32. But what that really says is 2 to what power equals 32. So that's what this log is saying. And kind of in an equation, we would write that as 2 to the x, so 2 to what power equals 32. And then we just have to think about this, right? So we do 2 times 2 is 4, times 2 is 8, times 2 is 16, times another 2 is 32. So our little x would equal 5 here. Okay, so log base 2 of 32 is equal to 5. And that's basically what we're going to do every single time. So over here, log base 4 of 2, that says 4 to what power equals 2. And that's a little tricky, right? How do I do that? So there's lots of ways. You might recognize that what we actually need to do is take a square root. And when we are in the exponential, you maybe hopefully remember that we can do that with exponents by doing a fractional exponent. So I know that x is ultimately going to equal 1/2 over here, but I could show you another way of doing it. I could actually take the 4 and rewrite it as 2 squared. And then when I have a power, I multiply. So 4 to the x is actually 2 raised to the 2x. And then that equals this equals 2 to the first. So I actually know that 2x has to equal 1, and then x would have to equal 1/2. So if you don't recognize that the square root is that, you can do it kind of this other way. All right? Next, 3 to what power equals 1? This is tricky, right? I can't do like a square root. That's not going to work. But what power always makes the exponent equal 1? And that's going to be 0. So if I do 3 to the 0 power, that's going to equal 1. In fact, if I do anything to the 0 power, it always equals 1. Okay, and we're going to get to some of these properties way down at the bottom. Here, number 4, log of 1 over 100. So the first thing you need to remember is just that, right, if we don't say what the base is, that it's always assumed to be 10. So what this really says is 10 to what power equals 1 over 100. And what I want to do here is rewrite this 1 over 100. Just like I did in the example right above, I want to try to write it in terms of a base of 10. Okay, so it's really 10 squared on the bottom. And if I can write it on top, that would be 10 to a negative 2, because remember that the negative exponents will bring things from the bottom to the top or from the top to the bottom. So ultimately I have 10x equals 10 to the negative 2. So then we can see that x has to equal negative 2. Okay. Log base 5 of the square root of 5, so that's 5 to what power equals the square root of 5. And we do the same thing. I wanted to rewrite that square root of 5 as an exponent. Okay, and then x equals 1/2. Over here, I have 7 to what power equals 7. So that has to be 1, right? Alrighty. So those are just quick examples. And now what we have down below are some properties. Okay, and these properties are super important to just kind of basically, I don't want to say memorize, but the better you know them, the better off you're going to be. So we start off with this one. It says log b of 1 equals 0. And we actually saw that up here with example 3. No matter what the base is, if you do the base to some power, so I'm just going to put an x for now, and it equals 0, that power always has to equal 1, which means that log base b of 1 is always going to equal 0. Okay? This property right here, the log base b of b equals 1, so I'm on this one, we actually saw that right here with number 6. So if you have log base b of itself, it's always going to equal 1 because we're always going to end up with this exact scenario where we have a number raised to a power equals itself. And so that power has to be 1. And gosh, I really hope you can see this yellow color. It's maybe not showing up all that well. Oh boy. Let's go to this weird blue color and hope that's a little bit better. The one over here on the left is actually very similar to number 5, okay? We have b, which is this base right here, raised to the x, has to equal this stuff right here, which is b to the x. Okay, so that makes sense, right? B to the x equals b to the x. So essentially, if you have log of some base like this, and it's raised to any old power, no matter what it is, as long as you have log base b of b, then this whole thing equals the power always. And I imagine you're going to have a little bit of questions on that one still, because people tend to have a little bit of trouble with this one and the next one. This is essentially the same idea. It's actually in exponential form right now because that log base b of x is in an exponent. So if I switch this to log form, it would end up being log base b, which is coming from there, of this x equals this entire thing over here. And this is true, right? Log base b of x would equal log base b of x. But essentially what you can think about, this is kind of like fake math, but that's okay, is that if you have b raised to a log with the exact same base, whatever's in that parentheses is what this is going to always equal every single time. Okay? Who's pumped for the next page? We're going to learn how to graph. It's going to be great. It's going to be super exciting. Oh my gosh, look at this. Most fun we've ever had. All right. So, first I'm just going to put this graph of log to the 2x on here. And I feel like I'm going a little bit slow, so I'm going to try to speed us up a little bit here. So, there's my horizontal asymptote. I know that when I do 2 to the 0 power, I'm at 1. 2 to the first is 2. 2 to the third is 4. And 2, that was 2 squared. Sorry, is 4. And 2 to the third is 8, which I can't see on the smartboard. So I'm hoping that I actually put that in the right point over there. And then you can go backwards, right? This point would be 1/2, 1/4, and 1/8, which is what these are talking about over here. Okay, so let me just fill these all in so that we are good to go. So when I was graphing this exponential, what I was really thinking of is I was doing distances from the x-axis. Okay? But really, I was doing distances from my horizontal asymptote, which just so happened to be on the x-axis. And so when I was 0 away, I just went up 1, because any base to the 0 power is going to be 1. When I was 1 away, I was just doing my base to that power. When I went 2 away, which is right here, I was doing my base to the 2nd power and then to the 3rd power. So when we're doing logs, it's very similar actually. We're essentially just flipping these values because that's what inverses do. They switch the x and the y's. But I'm going to ultimately do the same idea, but I'm going from a vertical asymptote. So I'm going to have distances from the y-axis this time, but really it's the vertical asymptote that I'm focusing on. And I'm just going to think of this as powers of 2 still. So I'm doing 2 to the 0 power is going to be 1. So this time, instead of going up, I'm going over. And then when I move up 1, I'm going to say 2 to the 1st power is going to be 2, so I go over 2. 2 to the 2nd power is going to be 4, so I go over 4. When I go up 3, that's saying do 2 to the 3rd power, that's over 8, which I can't see again, so I'm hoping I put that in the right spot. And then if I go down 1, it'd be a 1/2, a 4th, and an 1/8. So I'm just using the powers of 2 to help me graph that somewhat easily. And if you can understand that, then you can just use the transformations down below to help you figure out how to do all of this stuff, right? So we have the exact same notations that we're used to. If you have an outside value, it moves it up and down. If you have an inside value, it moves it left and right, but remember it's backwards. Outside reflects over the x-axis, so a vertical reflection. Inside reflects over the y-axis or a horizontal reflection, all right? So I'm going to just do some quick examples. If you feel like you're good at graphing, then you can do them and ignore me and move on to the next section. Whew. Who's having fun? No? Okay, just me. All right, inside value. That's going to move us to the right 1 place. Over here, I have an inside value that's a negative, so that's going to be a horizontal reflection. So I'm going to reflect over the y-axis, so side to side. And then here I have an outside value. This is going to move the entire graph up 4. Okay? So if I come back over here, right 1, what that actually does is it moves my vertical asymptote over 1 place. And from here, I can actually just graph everything normal. Just like I was doing up above, I can say my base is 2, so when I do 2 to the 0, I'm going to be 1 away from that. When I go up 1, I'll go over 2. When I go up 2, I'll do 2 to the 2nd, which is 4. When I go up 3, that's 2 to the 3rd, that will be 8, and then it will end up being a 1/2, a 4th, and an 1/8. Pretend like I could actually graph those accurately on a smartboard. And super easy to graph it, okay? I want to do the horizontal reflection. The exact same thing's going to happen, but instead of going right, I'm just going to go left. So I'm going to go left 1, left 2, left 4, and then left 8, which is hopefully where I put that. As I went, did 2 to the 1st when I went up 1, 2 to the 2nd when I went up 2, and 2 to the 3rd when I went up 3. Okay, and remember that you have the 1/2, the 4th, and the 1/8 if you need some more points to plot. Now when I go up 4, that doesn't affect my vertical asymptote. That's going to stay where it is. But what it does affect a little bit is I can actually kind of pretend like I move the x-axis up 4 places and that it's going to be right here now. Okay? This is that transposition of axes. This is the way that I really like to graph. I think I've mentioned that before. So when I was going over 1, and then I would say like go up 1 over 2, up 2 over 4, I was saying that from where this dotted line is now basically. So I can just put a point here, and then when I go up 1 from this dotted line, I can go over 2. When I go up 2 from the dotted line, I can go over 4, up 3, over 8. Okay? And I got someone knocking on my door, so I gotta pause. Alrighty, let's learn how to just solve some basic stuff here using the properties of logs that we kind of know already. So we have here, right, this is really a log base 10. So what this log says, log base 10 of x equals 3, really is just saying 10 to the third power equals x. All right, so we know that x is going to equal 1,000. Over here, we do the exact same idea. We say 2 to what power equals x? So it's 2 to the 6th power equals x. That's what this log really means. So remember that conversion I had on the first slide was that if you have y equals log base b of x, that's the same thing as doing b to the y equals x. So that's essentially the property that I just used to help me solve both of these things. All right. If I'm using my calculator, I can literally just hit the log button. So I would just hit log 8, and you get 0.9031. Over here, if I do this one, I'll just get negative 0.3665. Those were the hardest examples in the world, weren't they? All right. There's a very special base that we really like. It's base E, okay? And I talked about what E was in one of the previous videos, right? So I'm not going to really get into it, but this is all the same properties, right? We have ranges all real numbers, x is going to be greater than 0 for the domain, it's continuous, it's not bounded, because remember bounded means that it's above or below, and we're not being bounded above or below. There's no sort of symmetry on this, and we have x equals 0 is a nice vertical asymptote that we got going on here. And we have, as y approaches, man, I can't even talk. I'm not even going to erase that. We have as x is approaching 0, y is going to be approaching negative infinity, so that's what's going on right here. And then we have as x approaches positive infinity, y is approaching positive infinity. Got some general properties of Ln. So these are the exact same 4 ones that we had before with base b. Just saying that, hey, it works the exact same way. This is basically saying e to the 0 equals x, so that means that x value will always equal what? If I move over here, remember that this is really e, so this is saying e to the first equals e, so it makes sense that if we have ln of e, that it always equals 1. Same idea over here. This is saying that e I just did to the x power is going to equal e to the x. So if we have ln of e to the x power, it will always equal that x value every time. And here, very similarly, if I actually switch this into log form, because it's actually in exponential right now, so I do log base e of x equals ln of x, that should make perfect sense to you because log base e and ln are the same thing. So if I have e ln of 5, that's going to just equal 5. All right, so we got some quick examples of that. Just cruising along here. So remember, this is base e. So this is really saying e to what power equals the square root of e. Okay, so we know that the square root of e is really equal to e to the 1/2. So that means that x value has to equal 1/2. Using the properties that we have above, this is just going to equal 5. Same thing here. This is just going to equal 4. So that's this property. This one was that one over there. These last 3, we would use a calculator for the first one, right? So just put it in. This time we would hit the ln button. And then we would do it again. And here, if we tried, it wouldn't really work, right? Our calculator is going to give us an error, and that's because we can't have negatives inside. This is no solution. Whew, we're almost there. Last section. We have the change of base formula. So this really was helpful when you have older calculators. It's also helpful when you're dealing with stuff like examples 1 and 2 down below, where we're maybe dealing with some bases that we're not 100% great with. It says that you can rewrite this. Oh boy, running out of time here. All right, so if I have log base b of x, I can actually write it as log x divided by log b, and I can do that with any base I want. So that's what this is saying. So I could rewrite this as like log 2 of x over log 2 of b, and that would actually work perfectly fine. So I'm going to do these last 2 examples, hopefully before people start trying to come to the room. And what I want to pick is just what's a nice number that works with 8 and 4 here. And I think base 2 would actually work really nicely. So if I use the change of base formula, I can actually rewrite this with a new base of 2, and I'll get this. And now I can solve each part separately. This top part, log base 2 of 4, well, that actually just equals 2, because it's 2 to the 2nd power equals 4. And then down here I have 2 to what power equals 8? That's going to be 3. So log base 8 of 4 is actually just 2/3. And for example 2, I'm just going to change everything into the common base, so base 10. So I'm just going to say this is log 3 over log 2. This middle one is log 4 over log 3. And the last one is log 2 over log 4. And now I can just look for what I have in common. Here's a log 2, top and bottom. Here's a log 3, top and bottom. Log 4, top and bottom. So this whole thing equals 1. Woo! We made it. Hope this video wasn't terribly long, and I will see you in class.